Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 3 of the series on linear relations and continues with the ideas discussed in the previous 2 videos. We're going to be talking about parallel and perpendicular lines at this point. The symbol for parallel in mathematics is 2 vertical lines with a separator. Think about parallel, these 2 lines over here, as a straight north-south highway with a left lane and a right lane. Only a 2-lane highway. Let's say one that's going northbound and one that's coming southbound. These 2 lanes should never meet. And that's exactly what the word parallel means. When 2 lines are parallel, they cannot coincide or they cannot intersect. That's the formal definition of parallel. Two lines that will never at any point intersect are called parallel lines by definition. Then perpendicular lines. The symbol for perpendicular in mathematics is the upside down T, and it reminds you of a right angle. Okay, there should be like a little 90 over here, and of course a right angle means a 90-degree angle. The 2 words are synonymous. 90 degrees and right mean the same thing. So for perpendicular lines, think of a typical intersection in a city, like an east-west road intersecting a north-south road. They will normally intersect at right angles. At least in Toronto they do anyway. We're on a north-south, east-west grid over here in Toronto, so that's certainly the case. I mean, you're going to get some cases where the roads intersect at a non-90-degree angle, but that's fairly rare. Let's talk about parallel lines first. We have 4 cases that I can think of anyway. We have a case here where we have 2 parallel lines that are forward slashes. Or the second case where we have 2 parallel lines that are backslashes. Or the case where we have 2 vertical lines. Or finally the case where we have 2 horizontal lines. You'll remember that when we have 2 forward slashes, their slopes are positive. When we have 2 backslashes, their slopes are negative. For the vertical case, the slope is undefined. And for the horizontal case, the slope is 0. Let's look at this equivalent statement down here. This is called an equivalent statement. It reads mathematically L1 parallel to L2 if and only if M1 is equal to M2. The if and only if symbol, which is this right here, is also called a double implication symbol. It says that the left side implies the right side, and the right side in turn implies the left side. In other words, it works both ways. If L1 is parallel to L2, that implies that M1 is equal to M2. Likewise, if M1 is equal to M2, that implies that L1 is parallel to L2. So parallel lines have equal slopes. In other words, if 2 lines are parallel, then for certain their slopes are equal. On the other hand, if we know that the 2 slopes are equal, then the lines will certainly be parallel. We haven't proven this geometrically or algebraically. But for the time being, just take it for gospel truth, and we'll go on to perpendicular lines. Typically, perpendicular lines might be a forward slash coupled with a backslash. so that the angle that the intersection makes is a 90-degree angle or a right angle. In this case, certainly perpendicular lines will always intersect, whereas parallel lines will never intersect. Perpendicular lines, for certain, will always intersect. The other case is where you might have like a vertical line intersecting with a horizontal line. Again, that's a forward slash, so the slope is positive. That's a backslash, so the slope is negative. Over here, the slope is undefined, and over here, the slope is 0. Let's look at the equivalent statement for perpendicular lines. It says formally that L1 perpendicular to L2, if and only if M2 is equal to negative 1 over M1. So let's look at this in both directions, one direction at a time. This says that L1 perpendicular to L2 implies that M2 is equal to negative 1 over M1. Likewise, in the other direction, if M2 is equal to minus 1 over M1, then it follows that L1 is perpendicular to L2. So it works in both directions. Again, this is the double implication symbol, and it really means if and only if. Another way to write this is the following. If we cross multiply over here, it's clear that we get M1 dot M2 equals negative 1. So we get M1 dot M2 equals negative 1. So a slightly different form of this is this one over here. This says, again, we'll read it verbatim mathematically. It says that L1 perpendicular to L2, if and only if M1 dot M2 equals negative 1. Okay, in the forward direction, it says that two lines are perpendicular, implies that the product of their slopes is negative 1. Again, if two lines are perpendicular, that implies that the slopes are negative reciprocals. On the other hand, let's read these backwards. If the slopes are negative reciprocals, that guarantees that the two lines are perpendicular. If the product of the slopes is equal to negative 1, that's a guarantee that the lines are perpendicular. So to recap, perpendicular lines have slopes that are negative reciprocals or have slopes whose product is negative 1. Let's try to illustrate these ideas. Again, I'm not providing a proof of the parallel equivalent statement or the perpendicular equivalent statement at this point in time. I will provide an algebraic proof of each of these in a later video. I've seen quite a number of proofs that require geometry, and I'm going to try to come up with a couple of proofs that require only algebra. But I'm going to give you a feel for how a geometrical argument would go by bringing up a couple of rulers. Okay, that's my ruler that would indicate, let's say, L1. I'm going to bring it up there. And actually, I'm going to bring it a little bit closer. And there's L1. I'm going to bring another ruler up that's parallel to that ruler, and we'll call it L2. And let's see what happens over here. Let's consider L1 first. If we go over 1 unit of run, it generates 2 units of rise. Therefore, the slope of this ruler is 2 units. On the other hand, let's look at this ruler over here. If we go from this point to this point, 1 unit of run will generate, 1 unit of run will generate negative 2 units of rise. Okay, so the slope over here would be negative 1 over 2. Let's go over that again. Or actually, the slope would not be negative 1 over 2. It would just be 1 over 2. Okay, I'm already thinking about perpendicular lines, so I take it back. This is L1, L2. The slope over here, 1 unit of run, gives you 2 units of rise. And over here, we have 2 units of rise, 1 unit of run. So the slopes are identical. They both have a slope of roughly 2 units. Okay, so sorry about that. Let me take away these rulers here. And we'll introduce 2 rulers that are nearly perpendicular. So here's one ruler here. I'm going to let it pass through the origin. And here's a second ruler here, and I'm going to let it pass through the origin as well, the best that I can anyway. Okay, we'll call this ruler L1, this ruler L2. Let's have a look to see what the slope of L1 is. 1 unit of run, 2 units of rise. The slope must be 2. Over here, for the second ruler L2, we have 2 units of run, -1. If the run is 2 units, the rise is -1. If the run is 2 units, the rise is -1. So the slope of this ruler is -1/2. Again, I'll do it again. Let's look at L1. The run is 1 unit, the rise is 2 units. Slope is 2. Let's look at L2. The run is 2 units, the rise is -1 unit. Therefore, the slope is -1/2. Notice that 2 and -1/2 are negative reciprocals, or the product of their slopes is -1. So that confirms the perpendicular equivalence. Again, for the parallel equivalence, let's do it again. I hope I don't goof up this time. I don't even know why I goofed up last time, but anyway, maybe I'm just getting old. What are you going to do? Okay, anyway, these are 2 parallel lines. There's L1, L2. We go 1 unit of run, 2 units of rise. Slope is 2. And then we go 2 units of rise, 1 unit of run. Slope is 2 as well. So 1 run, 2 rise. Slope is 2. 1 run, 2 rise. And slope is 2 as well. So that indicates that that's sort of a geometrical argument that if 2 lines are parallel, then their slopes should be equal. We're going to run through a complete question now, Q2 in front of us. And it says characteristics of straight lines. And let's look to see what data are provided. We have P1 with coordinates -3, 4. That's a point on the Cartesian grid. And then we have another point P2 with coordinates 2, 3. And that's another point on the Cartesian grid. If we were to take a ruler to join up the 2 points, and then we would generate a line segment. If we extend that line segment in both directions, that will generate a line L. So these are 2 points on the line L. Let's see if we can get a feel for where these points are. We always start off at the origin. That's City Hall, if you'll recall. And this is like the city of Toronto. So let's look at P1. P1 has coordinates -3, 4. So we start off at City Hall. We go -3 and then 4. That's the point P1 up here. And then let's look at the point P2 with coordinates 2, 3. So again, we start off at City Hall. We go 2 units and then 3 units. And that's the other point P2. The objective now for part A is to find the midpoint between P1 and P2. So I refer to it as mid for midpoint, and then bracket P1, P2, which stands for the midpoint of the segment P1, P2. So when I write down P1, P2 with no comma, I mean the line segment. And we're trying to find out what the midpoint is. If you'll recall from the first video, and also the second video in this series, we developed a midpoint formula. And the midpoint formula says that the midpoint is the average of the x values. So it's -3 + 2 divided by 2. And we have the average of the y values. So it's 4 + 3 divided by 2. So the x-coordinate of the midpoint is the average of the x values, and the y-coordinate of the midpoint is the average of the y values. Now minus 3 plus 2 is negative 1, so we get negative 1 over 2, and 4 plus 3 is 7, so we get 7 over 2. So the midpoint should be at negative 1/2 comma 7 over 2. Negative 1/2 is really 0.5, and 7 over 2 is 3.5. So we found the midpoint, so no problem with that. The midpoint formula is easy. Average of the x's, average of the y's, crank them out, get the midpoint, no problem at all. Let's have a look at the slope. Little m stands for slope between P1 and P2. Or you can think of it as the slope of the line segment P1, P2. You'll recall the slope formula. It says y2 minus y1 over x2 minus x1. It's the difference in y values, delta y, over the difference in x values, delta x. So all we need to do is grab our y values. We have 4 and 3. So there's y2, there's y1, so we have y2 minus y1. And then x2 is 2, and x1 is negative 3, so we have x2 minus x1. So in the numerator, we have 3 minus 4, which is negative 1. In the denominator, we have 2 plus 3, which is 5. It's common to bring the negative sign in the middle. It just looks a little bit neater, so we conclude that the slope is negative 1 over 5. So that means, what does that mean? If we start off over here at the origin, we go 5 units to the right, and we go 1 unit down. So it would be this slope right here, the slope of this line segment right here. So it's 5 units to the right, 1 unit down. So it looks something like that. It's nearly horizontal, but it definitely is a backslash. Let's go on to the next slide. In part C, we're finding the distance between the points P1 and P2. And you'll recall that's given by the Pythagorean Theorem. The Pythagorean Theorem says that d squared is equal to delta x squared plus delta y squared. The delta x we can get from the slope that we just previously calculated, and the delta y, of course, is the numerator of the slope that we just finished calculating. So delta x is the denominator and delta y is the numerator. When you crank this out, you'll get 26. You can do this all at once in your calculator. There's no point in me going through all the details. The details are quite simple. Over here you get 5 squared, which is 25. 3 minus 4, which is negative 1. Negative 1 squared is 1. 25 plus 1 is 26. And then d is the square root of 26. Do not forget to take the square root at the end, and you'll remember that distance is strictly a positive quantity. So you don't ever write down d equals plus minus square root of 26, because distance by definition is a positive quantity. The next thing we'll do is find the point slope form. PSF stands for point slope form of the line. And you'll recall the point slope form is y equals m bracket x minus x1 plus y1. The m we already know is negative 1 over 5, and x minus x1 is just x plus 3, and then y1 is 4. Okay, so it's very easy to write down, no problem at all. Once you have a point, I could have used the other point as well. I didn't have to use P1. Let me see what point I actually used. Yeah, I wound up using P1. I could have used P2 with coordinates 2, 3. It would make no difference whatsoever in the final analysis. Just like if we go back to slope for a second, do you see we wrote down 3 minus 4 over 2 minus 3? If we multiply top and bottom by negative 1, this would read 4 minus 3 over minus 3 minus 2, and we get exactly the same slope. Okay? So as long as you do either y2 minus y1 over x2 minus x1, or you can do y1 minus y2 over x1 minus x2. As long as you keep the same order. If you keep 2, 1 on top, you have to keep 2, 1 on the bottom. If you keep 1, 2 on top, you have to keep 1, 2 on the bottom. Okay? Let's go on. Part E, we're going to find the slope-intercept form of the line. And essentially, all you have to do is expand and collect like terms in the point-slope form. So if we look at the point-slope form over here and we expand, in other words, we have a bullet and 2 targets. When we expand, we'll get y equals minus 1/5 x, and then minus 1/5 times 3 is minus 3/5, and couple it with the 4, and you get minus 3/5 plus 4. Once you simplify inside the bracket, it easily simplifies. We get 5 times 4 is 20, minus 3 is 17, so we get 17 over 5. And the result is y equals minus 1/5 x plus 17 over 5. There's the m, there's the b, and that's slope-intercept form. And then we'll go on. Part F says find the standard form of the line. And the idea here is just to manipulate the slope-intercept form. Or you can manipulate the point-slope form. Either one is all right. But we already have SIF. So we're just going to manipulate SIF to get the standard form of the line. So there's the slope-intercept form here. The first thing I said is move each term over to the left, move all left. When we move all left, we'll reverse the order. We get 1 over 5x plus y. When you move this over to the left, it becomes 1 over 5x, then plus y. When you move this over, you get minus 17 over 5 equals 0. Then what you do is put brackets around the entire equation and multiply right through by the lowest common denominator. Of course, the lowest common denominator here is 5. So if we multiply the entire equation by 5, we can clear the fractions. So that's what we're going to do. We get 5 times 1 over 5. That's just 1. And 5 times minus 7, or 5 times y is just 5y. And 5 times minus 17 over 5, the 5's cancel, and you get minus 17. So again, 5 times 1/5, you just get a 1. I didn't write it down. You get 5 times y, which is 5y. And then 5 times minus 17 over 5, the 5's cancel, and you get minus 17. Of course, 5 times 0 is 0. And this is standard form. We identify the A, B, and C as 1, 5, minus 17. We know the A is positive, so we're good to go. And we know that all 3 numbers, A and B, are coefficients. A is just a constant. We know that both coefficients and the constant are all integers, and A is positive. So that will constitute standard form. I know there are some textbooks or quite a number of students out there will move the minus 17 over to the right and declare x plus 5 dot y equals 17 as standard form. That's okay by me. I have no issues with that. I prefer having a 0 on the right-hand side. Myself, I don't mind the integers at all. That's great. I don't even care if the coefficient of x is negative. It really doesn't bother me one iota. But textbooks require the coefficient of x to be positive. That's just convention. There's no real mathematics behind that. It's just a question of form. Those are the so-called rules, but those are not mathematical rules. They're man-made rules. But in my standard form, I will always have a 0 on the right-hand side because that's my preference. Now we're going to calculate the x-intercept over here, x-int. And you'll recall that x-int is just minus b over m. And the b we found is 17 over 5. And the m is negative 1/5. And there's the minus sign. When you invert and multiply, you get 17 as the x-intercept. Alternatively, if you wanted to get the x-intercept, what we could use is standard form. You know at the x-intercept, the y value is 0. So you put a y value of 0 here, and you get x minus 17 equals 0. Therefore, x equals 17. Your choice. You can either use the equation itself to get the x and y intercepts, or you can use the little formulas that I developed for you to get the intercepts. It's completely up to you. Okay, that's all a matter of choice. So let's go on to the next slide. In the next slide, H, we find the y-intercept. Of course, we already found the y-intercept because we had points. We had slope-intercept form on our hands. But anyway, just to verify that the y-intercept is equal to b, and the b value is 17 over 5, we'll declare that as the y-intercept. The graph in front of you right here is a graph of the line that we were looking at, and the graph is generated by a software program called Maple, and Maple is a symbolic processor. So it's a symbolic math processor developed at the University of Waterloo, which happens to be the university that I went to as an undergraduate, and they did an excellent job developing Maple, and it's really quite an amazing program, and I would urge all students to start learning how to use it because it's an absolutely amazing program, and the learning curve is not extreme provided you know some mathematics. Of course, the more weak you are in mathematics, the harder it's going to be for you to learn how to use Maple, but you know, Maple is quite a bit easier to learn how to use than Mathematica, which is another symbolic. Actually, it's more of it's just another symbolic processor. But I find that the learning curve is quite a bit more steep. They're talking about slope. The slope is steeper for learning Mathematica than it is for learning Maple. Maple's a really good symbolic processor, and it's very intuitive, very easy to use for me anyway, and I use it all the time. So any computer-generated graph that you see in my videos was more than likely generated using Maple. So, you know, my hat goes off to you, the University of Waterloo. You're doing a great job. Anyway, your line should look like this. Let's look at point 1. P1 had coordinates minus 3, 4. And if you look, there's City Hall down here. So minus 3, 4. That's good. Notice the differential scaling over here between the y-axis and the x-axis. The x-axis is compressed and the y-axis is expanded. Okay, definitely a differential scaling there. It's not one-to-one, so beware of the scale. So the point P1 is negative 3, 4, and the point P2 is 2, 3. So no problem locating those 2 points. You'll recall that the midpoint was minus a half, 7 over 2. Which is minus 0.5, 3.5, and there's the midpoint right there. So the midpoint formula is working great. We found that the y-intercept was 17 over 5, and 17 over 5 is just 3 2/5, or roughly 3.5, thereabouts, and there it is right there. That's the y-intercept, and the x-intercept we found to be 17, and there it is right there. Again, the equation of the line was, I put it down over here in slope-intercept form, y equals mx plus b form, and we have y equals minus 1/5 dot x plus 17 over 5. And also down here, we found that the distance between P1 and P2 was the square root of 26. So if you measure the distance between P1 and P2, P1, P2, we should get the square root of 26, which is roughly the square root of 25, which is 5 units. Okay? And I think we'll do an over and out. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.